Hi, welcome back to Math 125 Introductory Statistics. This is week 6. We'll talk about probability. We'll cover chapters 13 and 14 this week. So we want to be able to basically define what does it mean to, what is probability, what does that mean to say something like, what's the chance that something's going to happen, what's the chance of getting a job, what's the chance of having rain tomorrow. So it turns out this is actually a tricky question because mathematicians have kind of struggled for a long time to define this theory in a rigorous way. And so this book we're going to talk about probability in the context of frequency theory, which works best for processes where you repeat some event over and over again and independently under the same conditions, and we want to know how often that event can show up. And so many games fall into this category. For example, gambling games. So here's a simple game of chance where we have a coin and we want to toss the coin, and we want to repeat this process over and over again independently in the same conditions, and we want to know what's the chance that either heads or tails will show up. And so the chance of getting heads is 50% in the long run. The chance of getting tails is also 50%. And then as another example, a die is a cube with 6 faces, labeled 1, 2, 3, 4, 5, 6. And so when I roll a die, the faces are equally likely to turn up. So chance of getting an ace, for example, which is a 1, is 1 out of 6, or 16 and 2/3%. And the idea is that if I would just roll a die over and over again under the same condition, then the ace will show up about 16 and 2/3% of the time. So this is basically the essence of frequency theory. So the chance of something gives the percentage of time that is expected to happen when the basic process is done over and over again independently and under the same conditions. And so another way to define that is to look at the number of ways that it can happen divided by the total number of possible outcomes. So this is known as the probability of the event happening. And notice that this probability is a number that is between 0 and 1, so it's a decimal or fraction. And then if I want to convert into a percentage, then that's how you typically we talk about chance as being a percentage. So again, if your answer is a decimal, then you can convert it by moving 2 decimal places to the right. So that chances are between 0% and 100%. And then the chance of something equals 100% minus the chance of the opposite happening. So this last thing here we're going to cover later today in the lecture. So we'll come back to that a little bit later. Okay, so let's do some examples here. Suppose you have a box that has some red marbles and blue marbles, and we're going to pick out one marble from the box at random. So that means each marble has the same chance of being drawn. If it's red, you win $1. If it's blue, then you don't win anything. And so you can choose between, say you can choose between 2 boxes. Box A contains 3 red marbles and 2 blue ones. Box B contains 30 red marbles and 20 blue ones. So the question here is, which box offers the better chance of winning? Or are they the same? So the mistake to make here is that look at box B and say, oh, well, there's actually a lot more red marbles. And so that maybe we have a better chance of getting red if there's 30 red instead of 3. But turns out this is actually the same. The 2 boxes give you the same chance of winning. In the long run, for example, each of the 5 marbles from the box A will appear about 1 out of 5 times. And so that means that for the red marbles, it will turn up about 3 out of 5 times. So that's 60%. Now in box B, even though you have a lot more marbles, it's the same because now you have 50 marbles, and the chance of getting red is now 30 out of 50, which is also 60%. So what matters here is that ratio, the number of red marbles divided by the total number of marbles, and so both of them have the same chance of happening. Okay, we want to talk about drawing tickets from a box, and we want to distinguish between 2 cases, whether we do it with replacement or without replacement. So you have a box of 3 tickets, 1, 2, 3, and we want to pick a box with replacement. That means that we pick out a ticket from the box, and then we're gonna draw 2 tickets at random with replacement. That means we pick out the first ticket, see where it is, put it back, and then pick the second ticket. So that means that with replacement means that we have to put it back, so that the second time we pick it, it's the same box as it was the first time. And then here's another thing that we might sometime do: draw 2 tickets, but this time we do it at random without replacement. That means that we pick the first ticket, see where it is, set it aside, we don't put it back, and then we pick the second ticket from the box, and this time is only containing 2 tickets. So again, with replacement versus without replacement. So again, with replacement you take it out and you put it back, and then without replacement you take it out but you don't put it back. Okay, let's talk about conditional probabilities. Let's talk about the cards. So we want to be able to understand what is a standard deck of cards. So in a deck of cards we have four suits. There are clubs, diamonds, hearts, and spades. The diamonds and hearts are red. The clubs and spades are black. And then besides the suits, there's also values on the card. So for each of the suit, there are 13 cards in each of the suit. So 2 to 10, these are numbers, 2 to 10, and then the picture cards are Jack, Queen, and King, and then there's also an Ace. So that's there are a total of 4 times 13, which is 52 cards in the deck. Because for every suit, there's 13 cards. There are 4 suits. Therefore, 4 times 13, which is 52 cards. So let's say we take a deck and shuffle it, and then pick out the top 2 cards, put it face down. You win $1 if the second card is the Queen of Hearts. So what's your chance of winning $1? So that's the first question. The second question is, if you turn over the first card and it's the 7 of clubs, what's your chance of winning? So let's answer the first part, which is that what's your chance of winning if we want the second card to be Queen of Hearts? Well, there's 52 cards and there's only 1 Queen of Hearts, so there's 1 out of 52, 1 over 52 chance that we get a Queen of Hearts. And then we don't really need to look at the first card, right? The first card doesn't matter, so it's the second card that matter, and the chance that the second card is the Queen of Hearts is 1 over 52. Now, if you turn over the first card and it's 7 of clubs, that means that one card is known, and now the question is, what's the chance of winning? Notice now that we have more information, the chance will be different, because 7 clubs is no longer possible. In other words, if I pick out the second card cannot be 7 of clubs, so the chance that the second card is a Queen of Hearts must be 1 out of 51, because again, that second card cannot be 7 of clubs. So now the chance go up a little bit. Okay, so what is conditional probability? So in the previous example, especially in part B, this actually, the 1 over 51 is actually a conditional chance. The problem puts the condition on the first card. It has to be a 7 of clubs. So a mathematician might talk about conditional probability that the second card is a Queen of Hearts, given that the first card is a 7 of clubs. So this is from the previous problem. So again, given that the first card is 7 of clubs, what's the chance that the second card is a Queen of Hearts? So this is conditional probability. So let A be the event that the first card is 7 of clubs, B is the event that the second card is a Queen of Hearts. And so the conditional probability for second card to be the Queen of Hearts, given that the first card was a 7 of clubs, is written like this, where we write P of B given A. In other words, given the A occurs, what's the chance that B occurs? And another notation we write is P of B, and then a vertical line, then A. So again, this is the same thing as the first, which is P of B given A. And so in this case, it was 1 out of 51, as we saw earlier. So that vertical bar is read as given. So this is some example of this conditional probability. So suppose that we pick a random day of the week, and the question is, what's the chance that it's a Monday? Well, there's 7 days out of the week, and so the chance of being Monday is 1 out of 7, or about 14%. Now, suppose that a random day of the week is chosen, but given that that day is a weekday, so suppose that we know there's a weekday, what's the chance that it's a Monday? So now this is different. We know there's a weekday, and there are 5 weekdays. The chance of it being a Monday is now 1 out of 5 instead. So the probability that it's Monday, given that it is a weekday, is 1 out of 5. So again, conditional probability means that we know a little bit more information. So now it goes up. It's now 20% instead of 14%. So given that it's weekday, the total possible days goes down from 7 to 5. A random day of the week is chosen. Given that it's a weekend, what is the probability that it's a Monday? Well, since we know weekend is either Saturday or Sunday, the chance of being a Monday is now impossible. So 0 out of 2, or 0%. Okay, let's talk about the multiplication rule. Given two events A and B, the chance that 2 things will both happen equals the chance that the first will happen multiplied by the chance that the second will happen, given that the first has happened. So this is the multiplication rule. It says that the probability that A and B happening is, we can do it 2 ways, either the probability of A times the probability of B given that A has happened, or we can do this another way, the probability of B times the probability of A given that B has happened. So this is the multiplication rule. So as an example, you have a box of 3 tickets, red, white, and blue. We pick 2 tickets at random without replacement, so we don't put it back. What's the chance of drawing a red ticket, then a white ticket? So let A be the first ticket being red, B the second ticket being white, and then to find the probability of A and B happening, in other words, the first ticket is red and the second is white, you find the probability of A, which is times the probability of B given that A has happened. The probability of A, the probability that the first ticket is red is 1 out of 3. The probability that the second ticket is white, given that the first ticket is red, is now only 1 out of 2. Because we know that the first ticket is red, that's 1 less ticket. The chance of the second ticket being white is now 1 out of 2. So notice that to find the probability of both things happening, we have to use conditional probability in the multiplication rule. So 2 cards will be dealt off the top of a deck. What's the chance that the first card is 7 of clubs and the second card is a queen of hearts? And so A, the probability that the first A is the event that the first card is 7 of clubs. B is the event that the second card is the queen of hearts. To find the probability of A and B, again we do P of A times P of B given A. But P of A, which is the probability that the 7 clubs show up, is 1 out of 52. Given that the first card is a 7 of clubs, so now we have 1 less card. The chance that the second card is queen of hearts is now 1 out of 51. So we multiply those 2 and we get the probability that both of them happening is 1 over 2652. Okay, let's do another problem where you have 2 cards that are dealt from a well-shuffled deck. What's the chance that both are aces? Again, A is the first card is an ace, B is the second card being an ace. To find the probability that both of them happening means that we have to find the probability of A happening times the probability of B given that A has happened. The probability of getting an ace on the first card is 4 out of 52 because there's 4 aces. But given that with the first card is already an ace, we now have 1 less card for the deck, which is 51. But we also have 1 less ace to get. So that means that the probability that we get a second ace, given that the first is an ace, is 3 out of 51. So this is about 0.5% to get 2 aces. Okay, let's talk about independence. 2 events are independent if the chances for the second given the first are the same no matter how the first turns out. Otherwise, the 2 events are dependent. So equivalently, 2 events A and B are independent if the probability of A given B is the probability of A. In other words, given that B has happened, that does not affect the probability of A. Equivalently, 2 events A and B are independent if the probability of B given A is the probability of B. In other words, even if we know A has already happened, that still doesn't affect probability of B happening. So 2 events are independent if what having one occurs does not affect the other one. We only have to check one of these to show independence between 2 events. So for example, if I toss a coin twice, if the coin lands on heads on the second toss, you win $1. If the first toss is a heads, what's the chance of winning $1? Well, If the first toss is heads, again, these are independent because if I toss, I get a heads the first time. The second time I toss, right, it doesn't matter that I got heads the first time. We have to reset the problem, and so really for both of these problems, well, we don't care what happens on the first toss, right? Because these are independent. So suppose you have two draw made from this at random with replacement from this box. We replace the ticket once we get it. Suppose the first draw is a 1. What's the chance of getting a 2 on the second draw? And then suppose that the first draw is a 2. What's the chance of getting a 2 on the second draw? And then the question is, are these draws independent? Okay, so whether the first is a 1 or 2 or anything else, the chance of getting a 2 on the second draw stayed the same. Okay, let's see why. So for example, if because we are replacing the card. Again, the key word here is that we're making two draws, we are replacing the card. So whether I get anything, I always put it back. So the chance of getting a 2 on the second card is independent of the first card. So this is this is independent because of the replacement. Okay, let's do another example, but let's do same thing as example 8, but this time we're gonna do this without replacement. In other words, we don't put anything back. So again, let's go back to this problem. Suppose that we pick suppose the first draw is a 1. What's the chance of getting a 2 on the second draw? Because we know the first draw is a 1, that is affected because we're not going to put it back. So now we have 4 cards, and there's only 1 now. The chance of getting a 2 is now 1 out of 4. 2 out of 4, right? Because we took out a 1 already, we don't put it back. The chance of getting a 2 on the second draw is now 2 out of 4. Now suppose that the first draw is a 2, and because we're doing this without replacement, we don't put it back. The chance of getting a 2 in the second time is 1 out of 4. So that means that notice that because of that, because it does matter whether we get a 1 or a 2 on the first draw, that means that these draws are dependent because notice the answer does depend on what happens on the first draw. So when we would draw with replacement, whenever we do it with replacement, we put it back, and then the events are independent. Without replacement, usually the answers are dependent. Each of the two boxes contains, say that this is now a new problem. Say we have 2 tickets. Each of the 2 boxes contain 10 tickets from 1 to 10, and 1 ticket is drawn at random from each box. Let A be the event that the number on the first ticket is a 6, and B is the event that the sum of the 2 numbers on the 2 tickets is an odd number. And so let's kind of talk about this problem in a few different contexts. So let's find probability of A and probability of B. So A is the event that the number on the first ticket is a 6. So the chance of getting A is, well, 1 out of 10, because we have 10 tickets, and then one of them is a 6. B is a little bit tricky. What's the chance that the sum of the 2 tickets is an odd number? Well, if you pick 2 tickets, you get a total of 100 different outcome, right? Because on the first ticket you have 10 possible outcome. On the second ticket you have also 10 possible outcomes, and 10 times 10 is 100. So of those 100 tickets, half them will add up to even, half them will add up to odd. So that the chance of getting the sum being odd is 50 out of 100, or 1/2. Now let's now ask: Are A and B independent? So again, A is the event that the first ticket is 6. B is the event that the sum is odd. The question now is: Are they independent? So let's do this by calculating both P of A given B and P of B given A. Again, you usually don't have to do one of them, but let's do both, just kind of see how we can do independence. And let's just show that these 2 events are independent. So let's do the first part, which is P of A given B. So given that B has already happened, in other words, that because B has 50 events, the sum being odd, given that that B has already happened, what's the chance of A happening? Of the 50 events in B, only the following are also in A, which is 6-1, 6-3, 6-5, 6-7, and 6-9. And the reason is because, again, we know that the sum is odd, so that means that one of them has to be even, one of them has to be odd. And because A is the event that the first ticket is a 6, to get A, given that B has happened, to get A, right, the first ticket has to be a 6, the second has to be odd, so it has to be 1, 3, 5, 7, or 9, because 6 is even. So that means that given B has happened, the chance of getting A is 5 out of 50. So again, given B has already happened, the sum being odd, there's only 5 choices that give you A, so it's 5 out of 50, which is 1 out of 10. So notice that this P of A given B is actually the same thing as P of A, because earlier we found a P of A is also 1 out of 10. So this shows that A and B are independent. But we're going to do this problem again just to kind of show that, let's do the other way, which is P of B given A, just for practice, even though we have shown that A and B are independent. So given that A has already happened, meaning that A is the following 10 events. A is when the first ticket is a 6. So these are all the events where the first ticket is a 6. So given that A has happened, what's the chance of getting B? Well, which of these add up to an odd number? Well, only these 5 events, 6, 1, 6, 3, 6, 5, 6, 7, 6, 9. So the chance of B given A is 5 out of 10. Okay, given the A has happened, there's 10 events. 5 of them is in B, so it's 5 out of 10, which is 1/2. So this again shows that P of B given A is the same as P of B. This confirms again that A and B are independent. So if two things are independent, the chance that both will happen equals the product of their unconditional probabilities. So this is a special case of the multiplication rule. So let me kind of explain this. So in general, the multiplication rule says this: P of A and B is P of A times P of B given A, or P of B times P of A given B. But if A and B are independent, then P of B given A is equal to P of B. So the above equation can be simplified to, so for example, if I were to use the first equation here, P of A times P of B given A, but P of B given A, the second part here, is the same thing as P of B. So we can simplify this to P of A times P of B. So this is actually very nice. It says that if you have two events that are independent, to find the chance that both of them happen, you just gotta find P of A and P of B separately and multiply them. So there's no conditional probability in this simplified multiplication rule. So this is nice. Whenever you have independent, you do it separately and you multiply, because they don't depend on each other. So there's no conditional probability. So let's do an example. A box has 3 tickets, color red, white, and blue. 2 tickets would be drawn at random with replacement. What's the chance of drawing a red and then a white? So again, because we're drawing with replacement, these are independent. So what's the chance of getting a red? Well, 1 out of 3. What's the chance of getting a white? Also 1 out of 3, because we are replacing our tickets after we pick it. So the chance of them both happening is 1/3 times 1/3, which is 1/9. So notice this is different than the example 3 earlier, where if you have independence, does matter, right? That when you have independence, it's easier to work out the probabilities because you don't have to worry about the other cases. Another way to calculate probabilities is actually to count or to list out the other possibilities. Sometimes, it's easier to, instead of using formulas like what we did, we can just count all the possibilities and just use that to find out probabilities. For example, suppose we throw 2 dice. What are all the possibilities? We hit all of them. The first die could either be 1 to 6. Second die could either be 1 or 6. And so we put them together, you get 6 times 6, which is 36 possibilities. And so sometimes, listing them out can also help us find probabilities. For example, if a pair of dice is thrown, what's the chance of getting 2 spots? Well, looking at this table here, the only way to get a total of 2 spots is this case, an ace and an ace. There's only one way to get it, so the answer is 1 out of 36. Well, how about the chance of getting a total of 4 spots when you add them up? So again, we list out all the possibilities. There's 36 total. The only way to get 4 spots is 1, 3, 2, 2, or 3, 1. So notice the order does matter. 1, 3 is different than 3, 1. And so there's 3 ways of getting a sum of 4, so the answer is 3 out of 36. Okay, here's another example where listing out helps. Suppose a family has 3 kids. What's the chance that they have at least 2 girls? Well, each kid, again, assuming that gender is binary here, this is just say boy and girl to make it simple. There's a total of 2 times 2 times 2, which is 8 different ways to have different genders. So we'll list out all the possibilities. Having at least 2 girls means either 2 girls or 3 girls, which means that we have, let's list them out again. Having 2 girls means either girl, girl, boy, girl, or a boy and then 2 girls. And getting 3 girls is only one way of doing that, which is 3 girls. So notice we list them out. We had there's 4 ways of getting 2 goods or 3 goods. So then the answer is 4 out of 8. So again, listing things out can be simple for some of these problems. Now let's look at this. We see this earlier in this lecture. Let's kind of explain it more. The chance of something happening equals 100% minus the chance of the opposite thing. So here's no way to write that. P of A is equal to 1 minus P of A complement. So this symbol A with the superscript C it means not A, or the complement of A. So this says that to find the chance of something happening, we can also find the chance of it not happening and subtract it from 1. So again, to go back to this problem, a family has 3 kids. What's the chance that they have at least 1 boy? Okay, at least 1 boy means either we have exactly 1 boy, which is these 3 cases: 1 boy, 2 girls, and then girl, a boy, and then a girl, or 2 girls and then a boy. So we have this is exactly 1 boy, and then this is exactly 2 boys. You can try different orders, and then this is exactly 3 boys. So to get at least 1 boy, you have to add them up, which is 7 out of 8. But notice that it's actually easier to this event A is actually hard to list. When you list out like this, sometimes you make mistakes. So it's harder to make a list like that. It's easier to look at the opposite event, the complement event. So if A is having at least 1 boy, not A means not having at least 1 boy, meaning you have no boys. So having no boys means all girls, and so that means that to find the probability of A, you subtract. You found the complement, which is only 1 way, and so you do 1 minus 1 out of 8, which is 7 out of 8. So again, the complement is much easier to compute, which is 1 out of 8. So that means that the opposite event must be 1 minus 1 over 8, which is 7 out of 8. Okay, here's another way to apply this idea. Suppose that the probability of winning the lottery is 1 in a million. Say you play the lottery every day for 50 years, which means that you play for a total of 18,250 days. What's the probability that you win the lottery at least once? Okay, so this is a case where, again, we want to use the complement idea. It's hard to list out. So again, let A be the event that you win at least once. It's actually impossible to list out, at least by hand, to all the ways that you can win at least once, because that means you have to win 1 of those times, or maybe 2 of those times out of 18,250, or 3 of those times. But each of those times it could occur in different days. By listing out all the ways you win at least once is really, really hard. But here's an event that's easier to think about. Look at the complement event, or the opposite event. The event that you win the lottery none of the time. So this is actually easy to compute, because that means that to get this event, that means you lose on the first day, and you lose on the second day, and you lose on the third day. You lose on all the days. Notice that these events are independent. Every time you play the lottery, it's independent. So we can use the multiplication rule. And because these are independent, it's actually easier to compute the multiplication rule. You simply multiply by all of these events. You find the probability of each of these events and multiply all of them. So the probability of you losing the first day is 999,999 out of 1 million. That's the chance of you losing on the first day. On the second day, it's the same. On the third day, it's the same. The chance that you lose on all days, you multiply all of them, because this is all independent, and so you get 0.982. This is the chance that you win the lottery none of the time. To now compute the chance that you win the lottery at least once, which is harder to compute, you just got to subtract this from 1. So 1 minus this is about 0.018, which is about 1.8%. So notice that it's really hard to win the lottery even if you play every day for 50 years. Only about 2% chance that you win at least once. Okay, 2 things are mutually exclusive. When the occurrence of one prevents the occurrence of the other, one excludes the other. So for example, if you toss a die, let A be the event that you get a 1 or 3, B is the event you get a 4 or 5. These events are mutually exclusive. If A occurs, then you cannot get a 4 or 5. Conversely, if B occurs, then A cannot happen. So pick a card. If A is a spades, B is a red card, then again these events are mutually exclusive. If you got a spades, then it's not red, and same thing, if you get a red card, then it cannot be a spades. Pick a card. A being a red card and B being a jack or an ace. These events are not mutually exclusive, because it's possible that a card is in both So it's possible that a jack is a red card, a red jack, like jack of diamonds or an ace of hearts. So these events are not mutually exclusive. So here's the addition rule. If A and B are mutually exclusive, then it's actually easy to figure out P of A or B. So it's the probability of A or B happening is P of A plus P of B. So or mean that either one or the other or both happens. Now if A and B are not mutually exclusive, then you have to use a more general rule, which is that P of A plus P of B minus P of A and B. So the key here is that we have to subtract the probability that both of them happens. So here's the reason why. If here's A and here's B and A and B are not mutually exclusive, that means that they have something in common. To find the probability of A or B, you have to add A and B. But notice if you add A and B, you're adding this intersection, this purple area here. You might be double counting and added it twice. That's why you have to subtract P of A and B, because when you add them, you add in this part twice. You got to subtract one of them out so that you're not double counting. So for example, pick a card. What's the probability that you get an ace or a spade? Let A be the event as an ace, B is a spade. Again, these are not mutually exclusive. You can have a card that is an ace and a spade. So to find the probability of A or B, you have to add probability of A and B, and you got to subtract the intersection of the two. So the probability of getting an ace is 4 out of 52. Probability of getting a spade is 13 out of 52. But it's possible they might get both, which is an ace of spade. So the probability of getting an ace of and a spade is 1 out of 52. So when you add P of A and P of B, you have to subtract the intersection here. So the answer is 16 out of 52. Okay, so here's a kind of recap of all the things we talked about today. Here's some equations to know. There's a multiplication rule, which says that P of A and B is P of A times P of B given A, or P of B times P of A given B. And so if A and B are independent, then this equation 1 here is simplified to P of A times probability of A and B is probability of A times the probability of B. So again, if you have independence, this multiplication rule is a little bit easier. There's no conditional probability. But in general, you want to apply the first equation, which is, in general, you want to take conditional probability. So the multiplication rule finds the chance that two things happen at the same time. Addition rule is so notice multiplication rule applies to the AND connective, but the addition rule applies to the OR connective. So the probability of A or B is the probability of A plus probability of B, and then subtract the probability of A and B. So but here's some special case as well. If A and B are mutually exclusive, then the probability of A and B is 0 because they can't happen at the same time. So this equation 2 also simplified to a simpler version, which is that P of A or B is equal to P of A plus P of B, assuming that A and B are mutually exclusive. So again, if it's mutually exclusive, this is simple, but in general, you want to apply equation 2 here, where you have to subtract the intersection. And the addition rule finds the chance that at least one of the two things happens. Okay, great. Thank you for watching.